So we're going to look at exponentials, which is the inverse of the logarithms. So let's have a look at the graph. And you may well remember the good old basic exponential graph. There it is. Starts off very shallow, so out at negative infinity it's close or asymptotic, giving it the technical maths word, to the x-axis. Passes through 1 on the y-axis, all of the basic ones do. That's as long as the base is bigger than 1. If the base is in between 0 and 1, then it'll go the other way around. Because between 0 and 1, of course, you have a fraction. So that's pretty much the same as saying a to the power of negative x, and a becomes a whole number. So that's why it goes the opposite way. So in other words, that red curve could be a to the negative x, where the base is in between 0 and 1, and the blue curve could be a to the negative x, where a is greater than 1. It's just you're playing with index laws, really. But there's our basic exponential curve. And from that we can work out interesting things like domain, all real x, range, y is greater than 0, odd or even function. Yeah, of course, there's no symmetry in the graph, so it's not odd, it's not even, or anything. Now, the one we're going to be really interested in is e to the power of x. Remember, e was that natural base of the natural logarithm. So when it comes to an exponential, obviously the graph looks like the red one, because you may remember e is around about 2.7. Hang on. There's the formula to work it out. The limit as n approaches infinity of 1 plus 1 on n, all to the power of n. So as you sub bigger and bigger but numbers in for n, you'll get closer and closer to the value of e. So as we get to infinity, if that was possible, we'd have the actual exact value of e. But there it is. 7182818. I was close. So on a calculator, it looks like it's a repeating decimal. But that's just because of the limit of your screen. If you had a bigger screen, you'd see that pattern stops. That it's actually an irrational number like pi, which keeps on going on forever and it doesn't actually repeat at any point. So if you wanted to work out e cubed on your calculator, well, you probably have to go second function or inverse depending on your calculator. You're still using that natural log button. If you notice above natural log, you'll see e to the power of x on there. So that's how you get, well, 3 for e to the power of 3 and so on. So you should get about 20.086 if you do that. Okay, we're interested in how can we differentiate things, how can we integrate things so we can actually use this function in some good practical problems. Differentiate exponentials, the world's easiest derivative. Watch this. If you differentiate e to the power of function x, how do you differentiate it? It's all to do with the power. So function x is going to be in the power, e is the base, so it's just a constant. You differentiate the power, you put it at the front. But be careful, don't change the power. This is not a polynomial. Remember with polynomials you subtracted 1 from the power? No, you leave the power the same for these ones. But you just differentiate the power, put it out the front. So e to the function x stays the same. Now, if the base is not e, you still pretty much do it the same way. So it's a to the power of function x, but multiply it by the natural log of a. So you still differentiate the power, put it out the front, but also multiply by the natural log of a. And that's all to do with the change of base rule in logs, is how you get it there. Very rare question. I mean, the vast majority will be base e that we'll be working with. Very rare you see one that's not in the questions. But if we do come across one, that's how we deal with it. Okay. So here it is, the easiest question you will ever see. Y equals e to the power of x. We're going to differentiate it. All right, so we differentiate the power. Differentiate x, you get
1.
Thank you. And then the power does not change. So the derivative is e to the x. It's the same. But that's actually quite interesting when you think about it. What that means is the slope of the curve, because remember the derivative measures the slope of the curve. The slope of the curve is always the same as the y value. So whatever the y value is, that's the slope of the curve. And that explains why that exponential curve gets steeper and steeper and steeper and steeper. Because the y values are going, so the slope is going up as well. Okay, e to the power of 5x. Differentiate 5x, you get, yes, 5 is the answer. So we get 5e to the 5x. Oh, this is a bit trickier. e to the 4x plus 3, differentiate 4x plus 3, you get? 4. So we get 4e to the 4x plus 3. Oh, now I've got you. The power is x squared plus 3x plus 2. Differentiate the power, you get? Remember to use parentheses because it's 2x plus 3. All of that times the e, and the power does not change. This is where your setting out's important. Because I know some people get lazy when they're doing their derivatives and they don't worry about writing y and y dx. They just go, oh, e to the 5x and the next line's 5e to the 5x. Distinguish between the two so you know exactly which one. Because in this case, if you have to go back and refer to it to find stationary points and what have you, if you haven't labelled which one's y, which one's dy dx, because it's always e to the power of the same thing, very easy to pick the wrong one if you haven't labelled it. So make sure when you're setting it out, label what is what. This is y, this is dy dx, and of course you could have a second derivative as well and things like that. 3x squared e to the 4x, we're going to have to use our product rule. So write down the first, 3x squared, differentiate the second, e to the 4x. Oh, exponential, we differentiate the power, differentiate 4x, we get 4. Yes, it's still 4. So we get 4e to the 4x. Plus, write down the second, e to the 4x. Diff the first, differentiate 3x squared, we get. It makes it a lot easier when I put the answers there for you. Hey, okay, let's tidy that up. 4 3s are 12. You're probably going to factorise that, depending on what you're going to use the derivative for. I mean, if I have to find stationary points, remember we make it equal to 0, so we need that to be factorised. By the way, if I did find stationary points, there would be stationary points at x equals what? 0 would be 1. Yep, because that x could be 0. Where else? Minus half because of the parentheses. Don't get caught out with the e to the 4x. Remember its range, y is greater than 0. It's never equal to 0. So the exponential part will never create a stationary point in the derivative because it can never equal 0. All right, anarchy. E to the 3x plus 2 to the power of 7, anarchy, which is, of course, bring down the power. Okay, come on. Bring down the power, 7. Lower the power, 7 becomes 6, and put the boot in. Diff the inside. And we get 3e to the 3x. Tidying that one up, 21e to the 3x, e to the 3x plus 2, all to the power of 6. Oh, quotient rule. Oh, we've got to do a quotient rule. We've done the other ones. Quotient rule, which is, of course, square the bottom. Square the bottom. That's the easy bit because you just go, whoop, squared. Square the bottom, write down the bottom, diff the top. Oh, the top, world's easiest derivative. Differentiate e to the x, you get e to the x. Minus, don't confuse that with the product rule, which is plus. Minus, write down the top, diff the bottom. Diff the bottom, oh, e to the power of x, world's easiest derivative. Differentiate e to the x, you get. Yeah, the answer didn't change from the last time I asked you. E to the x. All right, be very, very careful. E to the x times e to the x is good. Was anyone thinking e to the x squared then? That is a real common mistake. When people are working quickly, e to the x times e to the x, that becomes e to the x squared. Remember your index laws. Add the powers. So we have e to the 2x plus 3e to the x minus e to the 2x. Okay, those e to the 2x's are going to cancel, and we're left with 3e to the x on e to the x plus 3 all squared. Let's do a practical question. So we've got our curve y equals e to the 2x plus 1. What would that look like? We've got our basic exponential curve. By making it 2x instead of x, ooh, what's that going to do to the curve? It changes it horizontally, doesn't it? So we'd be pushing that in. That would make it steeper. But then we've also added 1. So we're going to shift the whole curve up 1 as well. All right, so at the point 1, e squared plus 1 would be the y value, the exact value for it. We're going to find the tangent. Okay, tangent is a line. Find the equation of a line. I need 2 things. Those 2 things are, I have a point. Yes. I need a gradient. Oh, haven't got one. But of course, we can find it because you just need 2 points and we can use our, oh, we've only got 1 point. Not a problem anymore because that's where we use calculus. All right, differentiate e to 2x, For some reason, this is now another common mistake people make. And they use 2e to the 2x for the slope. But remember, that's not the slope. That's the formula that allows you to find the slope. At the point, x equals 1. So when x equals 1, the derivative would be 2e squared. So the slope is 2e squared. We have a point, we have a slope. Y minus the y value, so all of the e squared plus 1, equals slope, 2e squared. Outside of x minus 1, we expand that all out. It looks horrible, the final answer, but it is what it is. There's our equation. And it is a line because it's a constant times x, a constant times y, and a constant by itself. Yes, those constants involve e, and they're irrational, but it still satisfies the condition. That is a straight line. So 2e squared x minus y minus e squared plus 1 in general form. All right, here's one where the base is not e. And if you remember what I said was, it's okay, we'll do it exactly the same, but we will also make sure we multiply by the natural log of the base. I advise putting parentheses around that, because otherwise you can see it would be, if I didn't have it there, it would be easy to confuse that to be 44 to the power or something like that. So I'd probably put parentheses around that to make it very clear. So 2x log 4, 4 to the power of x squared. Y equals, we're going to differentiate log of x. Huh? We know that answer anyway, because we did that last year. But let's pretend that we don't know the answer. Well, if y is equal to the log of x, I'm going to make x the subject. So I have to undo the log. To undo a log, I must do the opposite to both sides. So the opposite or the inverse of log is exponential. So it becomes x equals e to the power of y. Okay? So I've exponentialized, if there is such a word, both sides. So x equals e to the y. I can now differentiate that because we know how to differentiate exponentials. But instead of finding dy dx, I'm going to find dx dy. And dx dy would be differentiate e to the y, world's easiest derivative, e to the y would be e to the y. But of course we're trying to find dy dx, not dx dy. All right, I'll turn both sides upside down. There's the derivative, but it's in terms of y rather than in terms of x. Now if we want to get the answer that we had before, all we've got to do is look at, oh, hang on a sec, x is equal to e to the y. And there's the answer that we would have got before, 1 on x. Okay? So it actually does work. We could convert all of those log, not that I'm suggesting you do it that way, but we could, all of those log ones that we had to differentiate, we could turn them into exponentials and differentiate those and come up with an answer. All right, 13a, 13b, oh, not 18. See, I'm not mean. Get you to do all the even ones, just not 18, okay?